Hey everyone, so this is the last topic for modern physics where we're going to talk about energy levels. Now, you should have learned a lot of this stuff before in um, chemistry. It's a little bit of a recap, and we kind of mentioned it before in the uh, earlier part of modern physics where kind of talked about the Bohr model a bit. So, if you recall in chemistry and from before with the Bohr model, the main idea is that electrons are orbiting at these very specific orbitals and they can jump between the orbitals by either absorbing energy or releasing energy. If they absorb energy, they go up higher into the orbitals, and if they release it, they go down lower. So essentially, the lower in the orbital they are, the closer they are to the atom, sorry, I should say the nucleus of the atom, the less energy they have. And the energy is always going to be released in the form of a photon. So it's either going to absorb a bit of light or it's going to emit a bit of light during these jumps. So the one thing about this is that the amount of energy required is very specific to the orbital that's jumping, as well as even the what type of element we're dealing with. Jumping from the n equals 1 to n equals 2 orbital for hydrogen is not different than helium. Um, what we would do is typically we'd have what's called an energy level diagram, and this basically shows the energy difference between all the different orbitals. So there's two diagrams on the reference table uh, that you have. There's going to be a hydrogen one and a mercury one. There's really no way that you could ever confuse them because if you notice, the hydrogen has numbers n equals 1, n equals 2, n equals 3, so on, all the way up to infinity. The the mercury one, on the other hand, has letters A, B, C, D. So there's absolutely no way you'll ever be able to confuse these. One thing to note, you'll see some key terms here. First, they'll have the lowest possible state the electron can go in is usually called the ground state. So this is almost like um, I think one of the ways that they describe this on questions a lot of times is they say that it's non-excited. It's like the base level. It's where the electrons are normally sitting. If you look over here, though, this n equals infinity that they wrote, they label this as the ionization. If an electron gains enough energy to get to this level, that means that the electron is now free from the grips of the atom and can move wherever they want. So that's where ionization comes from, where the electron finally leaves the atom's grips and the atom is now not negatively charged, positively charged. Another thing you'll notice is that there's numbers here. These numbers are the energies of the different orbitals, all measured in EVs. So, what you have to make sure you do is that if we're going to use our other equation from, E equals HF to find the frequency, we need to make sure we convert this energy back into joules. So I'll bring that up again in a second. Another thing that you'll note is that all these numbers are negative. You don't really have to worry about it. It's really just set so that they could set the ionization equal to 0. If you recall from the electrostatics topic, the conversions we use to go from EVs to joules is this. 1 EV equals 1.6 times 10 to the negative 19 joules. If we have the number in EVs, we're going to multiply it by this number. If we have the number in joules, we're going to divide by this number. I always think about the units. If I want joules, and I don't have it already, I'm multiplying it in. That way I can get the joules. If I have joules and I don't want them anymore because I want EVs, I have to divide the joules out. So whatever helps you remember which way to go, you know, keep that in mind. Um, there's an equation on the reference table to figure out the energy of a photon. It's kind of a useless equation. It's E photon equals E initial minus E final. You'll notice that this is actually flipped from some of the other things that, anytime you take the difference between two things, it's always final minus initial. The reason it's flipped is just because of the fact that the the energy signs are negative. It honestly, it doesn't even really matter if you use this order. You don't need to really worry too much about whether or not the numbers are placed in the right spot. What we really care about is that you just take the difference between the two levels. So, for example, let's say that we were doing a problem where an electron went from the ground state to its first excited state, which is n equals 2. So, what we would say is we would use the equation. We would say that we're doing the energy at the first level minus energy at the second. We take the numbers that you see on the reference table for n equals 1 and n equals 2, plug them in, take the difference, and we get negative 10.2 EVs. So basically, what this is saying is that the negative tells me that I absorb the 10.2 EVs, and the electron now jumps up to the higher level. So this 10 EV energy is absorbed, electron jumps and becomes excited. If we did this opposite, so it goes from n equals 2 down to the ground state, the numbers get flipped. All you see is that this number is still the same. It's just now it's a positive number, meaning that that energy now got released. So this is why I said it doesn't really matter if you actually put the numbers in the right order, because the overall number, the absolute value, the magnitude of it will always be the same. The only difference is the sign, and that's something that you could put in at the end. If you know that the energy was absorbed, you slap on a negative. If it was released, you make it positive. But honestly, I can't really think of a scenario where sign actually mattered. So I wouldn't really stress too much about it. Again, the main idea is that you find the two levels that you're looking at, take the difference of them, and that's your energy. But again, note that it's in EVs. You're gonna have to convert to joules if you're trying to figure out what the frequency is. One thing to note is that the electrons can only jump if that we have that exact amount. So, for example, back here, to go from 1 to 2, we found was 10.2. To go from 1 to 3, on the other hand, what we'd have to do is do 13.6 and minus 1.51, which is the energy of the third state. So to go from 1 to 3 would require 12.09 EVs of energy. That means if I send a photon towards this hydrogen atom that was a number between 10.2 and 12.09, like 10.5, this electron will not jump. It can only jump if it gets the exact amount, no more, no less. Um, so the analogy that I use is sometimes saying that the electron needs exact change. It cannot break a 20. It can't have a little left over. That's not how it works. It doesn't get a tip. It's got to get the exact amount in order to jump, and that's it. The only time it's actually allowed to get more than what was put in, or more than what's needed, I should say, is when it goes to become ionized. If we have an electron here that goes from the ground state to the ionization state, so in this case it would be, I would need about 13.6 EVs. Any number beyond 13.6, the electron can absorb. And in that case, any excess energy actually gets used as kinetic energy. That's the only scenario where the electron is allowed more than what's needed. Any other case, as long as it stays within the bounds, I guess you could say, of the atom, it needs exact amounts of energy, exact change. All right, so here's the first question. Pause the video, work itself. We'll go over in a second. All right. So for the first question where it says which energy transition could produce this, honestly, you have to just kind of subtract around. Clearly, it's not n equals 1 to any other state, so we're looking most likely at n equals 2. So do subtraction between all these, and you'll see that the choice is n equals 6 to n equals 2. Now, the reason I'm saying n equals 6 to n equals 2 is because the photon was emitted. So again, that means it's dropping down from a higher state to a lower state. If it was absorbed, then it would be the other way around. And yes, you will have to keep track of this. Multiple choice questions pop up all the time where they'll have n equals 6 to n equals 2, and then another choice would be n equals 2 equals to n equals 6. So they love throwing this combination. So you want to keep track, is the photon being emitted or is it being absorbed? Is the electron jumping up or is it jumping down? All right. Now to find the energy in joules, since this number is in electron volts, we're just going to multiply it by the 1.6 number, that magical number that we're going to constantly be using. And we get that it's 4.83 times 10 to the negative 19 joules. Now we have to determine the frequency of this. So we go back to our first equation from this unit, E equals HF. So take our new energy in joules, divide it by Planck's constant, and we get 7.29 times 10 to the 14 hertz, which might be in the ultraviolet range, I think. I'm not too sure. And that's pretty much it for that. Again, the main gist is you want to make sure that you know how to convert from EVs to joules. And remember that you can never use this number in the E equals HF equation. In fact, you are not allowed to use EVs in any equation whatsoever. All right, here's the next question. Pause the video, work itself, and it'll go over in a second. All right, so here we have our mercury atom. They want to know what the energy is in joules as it goes from A to G. So again, we look at our reference table, we look at the diagram, write down the two states. A is 10.38, G is 2.48. So the energy is going to be 7.9 EVs. Multiply this by that magical 1.6 number, and we get 1.26 times 10 to the negative 19 joules. Notice I'm dropping the negative because I don't need it here. I already know that the electron was absorbed in this case, so I don't really need to worry about it. If you want, you could always tack on the term absorbed, but like I said, it's not a huge thing. And then part B, they want the frequency of this. So again, now that I have this energy in joules, I plug it into E equals HF, just plug and chug, and I get my frequency to be 1.91 times 10 to the 15 hertz, which I'm pretty sure is also in the ultraviolet range. I'm more definite about that being in the ultraviolet range than the other one. All right. And then the next one. Here's the next question. Pause the video, work itself. We'll go over in a second. All right. Once again, they tell us that we go from the ground state and we get 10.2 EVs. So the state that we go to, we're just going to add this number to my original negative 13.6. I get negative 3.4, which is right here, n equals 2. So clearly it's being excited to that first excited state, n equals 2. They want the next part, they want the energy in joules, so this is just a conversion. 10.2 EVs multiplied by 1.6, and we get 1.6 times 10 to the negative 18. And then again, they want the frequency, so plug it into E equals HF, plug and chug, get 2.46 times 10 to the 15 hertz. All right. So again, you should start to see the pattern. This is actually one of the main reasons why I've said that the modern physics topic, the way it's covered in regions, is very basic, very straightforward. Is mainly because, as you can see, everything's given on the reference table. It's simple math, adding and subtracting numbers, plugging into equations, nothing crazy. The toughest part is just converting, knowing when to multiply and when to divide. You're going to see questions where it's like this, and then questions where they go backwards. Maybe I'll give you the frequency, and you have to tell me the energy. And then you have to tell me the energy in EVs. And then you have to figure out which transition that relates to. So you should be able to go frontwards and backwards. Here's the next question. Pause the video, work itself. I'm going to go over a second. Okay, so they tell us that the electron is located at the C energy level, which is right here, negative 5.52, and we have to get to the ionization level, which is 0. So we take the difference between those two, and 5.52. So really quickly, you should notice that all these numbers are basically telling us how much the minimum energy needed to ionize them. So you don't even need to really worry about the minus 0. Just read that number, and that's how much energy would be needed at minimum to ionize it. Because remember, technically the electron can absorb any number above this as long as it would become ionized eventually. Um, all right, so then the next part, to find the energy in joules, we take the 5.52, multiply by the 1.6 number, and we get 8.83 times 10 to the negative 19 joules. From there, we can find the frequency by using E equals HF, plug and chug, and we get 1.33 times 10 to the 15 hertz. Um, it comes up every now and then. It's a very rare question, but it does happen. So I'll mention it now. For the most part, visible light, it's not super common in a lot of these. It usually is about 1 to 2 EVs ish. Three, if you get something a little bit above 2 EVs, it might still be in the visible light spectrum. You just want to kind of keep an eye out for it that the visible light energy in EVs is fairly low. So again, somewhere between 1 and 3. Um, they've asked this a few times where they'll ask which energy jump would release visible light. And if you don't remember how much energy visible light has in EVs, basically what you'd have to do is go through each scenario, figure out the EV jump, convert that EVs to joules, and then use equals HF to figure out what the frequency is for each one. And if you're lucky, you picked the energy for you picked the choice that was visible light from the get-go. If you're unlucky, you have to do 3 scenarios first before you figure out which one's the real answer. So sometimes it helps just to remember that like 1 or 2 EVs is usually visible light. Anything beyond 3 is in the ultraviolet range. And I'm not too sure if anything is in the infrared spectrum. Um, it would probably be something like H to I, which is really small. All right, here's the next question. Pause the video, work itself. I'll go over in a second. All right, so here it says that the electrons at the n equals 3 state, and it's going to drop down, and they want to know how many different frequencies there are. Now, this one's a little bit tricky. I had mentioned that the electrons can jump from one orbital down to another orbital. So, for example, normally we would go n equals 3 straight to n equals 1. However, that's not always the case. The electrons don't always have to take the immediate straight path to the ground state. While they will eventually reach the ground state, they could always take a scenic route where they stop off at other energy levels. So, for example, if we had an electron at the n equals 6 state, instead of jumping straight to n equals 1, it could maybe some electrons decide to jump to n equals 5 before going to n equals 1. Or maybe they go to n equals 3 and then down to 1. Or maybe 3 down to 2 down to 1. So there's a bunch of different combinations that can happen as the electron drops from one level down to another. So it turns out that at the n equals 3 state, there are four. Oh, wait. I thought that was explaining it. The answer is that there are going to be 3 different frequencies. So the first frequency is going from n equals 3 straight down to n equals 1. So that's one frequency. The next one would be going from n equals 3 down to 2, and then from n equals 2 down to 1. Each one of these is unique and has a different amount of EVs attached to it. I'm not going to do the math, but you can probably guess what the numbers would be about. So as the electrons jump from n equals 3 to n equals 1, there are 3 different frequencies that are going to be released. Because again, Some of the electrons are going to go to 1, some are going to drop to 2 before going to 1. We could take this one step further and ask, well, how many ways can we have it at n equals 4? Well, this number does start to balloon up as we go higher and higher. Um, I would recommend that you all try to see if you can figure it out, because it is actually, in my opinion, a little bit fun trying to find all the different combinations. And it's important to remember that we're looking for unique frequency combinations, not just how many different ways. So I'll just go through them right now. So there's 1 going from n equals 4 to 1. I could also go from 4 to 2 and then 2 to 1. I could also go 4 to 3, 3 to 1. In addition, not only can I do 4 to 3 and then 3 to 1, I can do 4 to 3, 3 to 2, 2 to 1. Now, right now, you may see that I have 1, 2, 3, 4, 5, 6, 7, 8 lines drawn. However, as I mentioned before, some of these are not unique lines. Like here, I have n equals 2 to 1, and I have it over here as well. So I'm not going to count that one. And same thing for the n equals 4 to 3. I have it appear a second time, so I'm going to have to cross that out. So my answer is 1, 2, 3, 4, 5, 6. There are 6 unique frequencies that could be released going from 4 to 1. Um, if you want, you could try at higher levels. Again, seems a little interesting. I always like doing this and trying to catch the duplicates. Of course, this is something you'd actually have to write out, and it's not really something that you could do in your head very easily. All right. All this actually leads into the idea of these energy spectrums. The fact that atoms, different elements, have different locations for their orbitals means that the energy jump between each orbital is going to be different. And it's going to be specific to an element. So it turns out that if we took all the light that gets released or absorbed by an element, we would get a very specific line spectrum that represents that element itself. So, if we have a hot object like the sun, we get a continuous spectrum of all the different colors. If we send that light through, oh, actually, that would be this one. If we send light through the like a gas of some element, uh, some of those atoms will absorb certain frequencies of light. So we get these absorption lines where we're missing the color of certain frequencies. If we instead excite them, maybe we send some electricity through the gas to kind of charge up those electrons, we'll start to get emissions of the light, and we end up getting these bright bands of colors along a black background, and these would be the emission lines. So this is just kind of going through the whole thing again. That continuous spectrum is all the colors. Emission spectrum is only released by the atoms, and absorptions is, everything but what gets absorbed by the atoms. And notice that the lines for both are basically symmetric. And as we mentioned, the emission absorption lines are specific to each element. This is actually how we're able to figure out not only the composition of what's in the atmosphere of different planets, of different stars, but it's also how we're able to tell whether or not galaxies are moving towards or away from us, because we can identify the lines that match up for hydrogen, since no other element here has lines that match exactly with hydrogen's lines. And then if we notice that instead of them being here, they're drawn here and here, then that means that it would be moving towards us, because those lines shifted towards the purple side, towards the blue. It got blue shifted, so it's moving towards us. They shifted the other way, then it's moving away, red shifted. So yeah, this is just an example. Here we have a normal line spectrum for some element. Maybe this is hydrogen. And then we could see this example where all these lines are shifted over to the left towards the red. So this is moving away from us. This is red shifted. Uh, then the third one, all these lines are shifted over to the right. So these would be blue shifted and it would be moving towards us. If we want to take it one step further, we could actually figure out how much of a difference these lines changed and use this to figure out the actual speed of the motion. You know, how fast are they moving towards us, or how fast are they moving away from us? It's using this process that we know when Andromeda galaxy is going to collide with us. We know for a fact the moment it's going to happen because we know the Andromeda speed. We know how fast we're getting closer to each other. We know how far apart we are. So it's easy to calculate. You know, doesn't take a rocket scientist. All right. There's not that many questions with the light spectrum, so this is like the only example. So pause the video, work itself. We'll go over a second. All right. They want us to know which elements make up this unknown sample. So the idea is that we have to go through and match up the line spectrum for each element. Element A has these two lines which don't appear, so element A is off the table. Element B has this line and this line matching, so this one is definitely one of my elements, but there are a lot more, so I need to figure out what they are. C seems to match, this line matches, and these two. So C is most likely my next element. Let's just double check with D. D shares this line, but these two lines are not, and these two are not there, so D is off the table. So my answers would be elements B and C. And that's it. And in fact, that's actually it for all this stuff. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.